Hello everyone, and welcome back to another Eng130 video tutorial. Now, originally we were only planning to do two videos for Centroids, one covering continuous body and one covering composite body. But due to this week's assignment, I've decided to come out and include a third one, and that is finding the centroids of 3D shapes. So instead of a DA, you have a DV, and we have to find volumes instead of just the areas of a slice. And to make it even easier for you guys, is the example that we'll be doing is the one right from your homework. Or at least if you're in the fall 2019, it'll be right from your homework. So I've had at least 30 students come talk to me about this example, and it's a little bit challenging, but you guys have the tools to solve it, and we'll go through it together, and hopefully it can help. And if you guys notice this example before the due date, you can get some extra marks on your assignment. So with that being said, let's jump into the example. Alrighty, so looking at this example, it says a solid is formed by revolving a trapezoidal area in the first quadrant 360 degrees about the y-axis. Determine the y-coordinate of the centroid for the resulting volume. So basically this is a 3D shape, and it's a really ugly 3D shape, but I'm going to try and draw it so you guys can kind of understand exactly what it looks like. So we have a circle or an oval. Oops, perfect. And then inside we have another oval. And then what this does is this shape, let's see. So I'm not a good artist, but hopefully this will kind of show you guys what we're dealing with. So we're dealing with a shape like this. So inside of this shape, which I'll draw in red, there's a hollow core. And oops. And this hollow core is also at a different angle. So this one's not straight down. It's at an angle as well. So this is kind of the shape that we're dealing with. And as you guys remember, for 3D shapes, we need to find a slice. It's just like 2D shapes, where we need to find a slice in order to satisfy the formula. And the formula for a centroid for a 3D shape, actually I'm just going to move all this over to the side a little bit, like this. So if you guys recall, the formula for a 2D shape, so I'll put just 2D right here so you guys can see exactly what I mean. So for a 2D shape, y bar is equal to the integral of y squiggle dA divided by the integral of dA. So in this case, the main thing that we had in this formula was dA. And what dA is the area of our slice. However, for 3D, which is what we have here, the integral changes a little bit. It's going to be y bar is going to be equal to the integral of y squiggle, so that first part doesn't change at all, except instead of dA, since we're in 3D, we have a dV. And this time, this means the volume of our slice, so the integral of dV at the bottom. So now we're faced with kind of two problems. Problem one, y squiggle, well, what's that equal to? And the second one, dV, what's this equal to? So this is what we're going to have to try and find out. So the first thing that we need to do is we need to take our slice. And just like all the other 3D examples that we covered in class, or at least hopefully the other professors covered in class, because I know I did, is we have to take a nice slice. And the slice usually goes like this. So this is going to be our slice, like this. And then keep in mind that somewhere in the slice it's also hollow. So our slice is going to look something like this. Hopefully that kind of looks fine. So again, this will all be filled in around here. And then it has a thickness. So the thickness of the slice in 3D is always going to be whatever variable we want. So if it's the y centroid, this is going to be dy. So that's always true for the case in 3D. What else is always nice for the case in 3D is, excuse me, is our y squiggle. So again, the bottom axis is down here. So this is the bottom axis, the y-axis. So therefore our y squiggle is going to be the distance from that axis to the centroid of the shape. So in this case, it's actually just the distance from the axis to our slice. So this is y squiggle. So therefore y squiggle is just going to be equal to y. So far this isn't so bad. It's now finding the volume of the slice that's the problem. If this was just a regular equation, or sorry, just a regular solid shape, then all we would have to do is find an equation for one of the lines, and then we can just use our formulas for a circle. However, in this case, it's a little bit more complex than that. So what I'm going to do is I'm going to draw the cross section just like they had it. So what we're going to do is this is going to be our axis. And then I'm going to draw the cross section in green. So the cross section, we have one, kind of goes up like this. And then we have another. So this is not going to be to scale by any means at all, but we're going to just work with it. So let's say that this is our cross section. And if we go up here, we can start dimensioning it. So let's say that this one, oh, I did this wrong. It's not going to work out too nice. All right, so I'm going to try and make it at least somewhat good. Actually, I'll just use the actual dimensions. So we got 30, 10, and 20. So we'll go from here to here. And then it's 40 tall. So we go from here to here. And this one's 30 across, here to here, and then we can just connect them. So this is the actual thing, and if I just throw in some dimensions just to show you guys, this one should be 30 and 30. The bottom one is going to be 20 and 10. 20 and 10. And of course the height of it is going to be 40. So this is what you guys need to look at right here. Is you can't think of this as a trapezoid. It says trapezoidal area, and I think that's what kind of screwed most of you over, is you guys all went to the formulas for trapezoids, and I'm not gonna lie, I did it too. This question even took me a little bit by surprise. That's why I thought maybe a video would help shed some light on this terrible situation. So this is exactly what you're going to have to think of. You're going to have to think of it like this. This curve we're going to have as y1, and this curve is y2. We're going to have to think of these as just separate lines, and we want to find the area between them. Just like a 2D case, when we're given two lines, we want to find the area between them. So for this right now, let's just forget about this line right here. Let's pretend that this was our shape. So our shape came all the way to the end. And if we knew that y1 there, actually I'm going to put this as y2 because it's further out. So this one's going to be y2. And if that's y2, that means that the distance, the distance from the axis to a point on here is going to be x2. So what this means is that the radius of this cone or cylinder, whatever you want to call it, is always going to be x2. So the volume here, or actually, yeah, we're not going to do the volume right now. So if I were to take a slice in 2D, so let's pretend that this was just a slice in, a slice in 2D, right here. What we can kind of see is that x2 is going to be the radius. So if I come up here and look, and I want a 3D slice, and I'm considering the whole purple region, it's basically just a cylinder slice. So I know that my dV, and it's going to get really confusing, the dV of this slice right here, if there was not a hole, if there wasn't a hole, it'd be pi r squared, and then that's the surface area, and then times the height of the slice. And the height of the slice is dy. So this right here is for the slice. So assuming that there was no hole in it, I'm just taking the radius times pi, and well, pi r squared, so that's giving me the surface area of the slice, and then timesing it by the height, dy. But now from this figure above, we know that the radius is actually x2. So we can go pi x2 squared times dy. So right now, this is the whole area of the slice if we didn't consider the hole. But now we have to consider the hole. So when we come back to this diagram right here, we're going to erase this, and we're going to acknowledge that there's actually a line from here to here. And what's nice is if we call this one y1, then this distance from any point on the axis to here, this is going to be considered x1. So now we can find the area of this region right here, which I'll highlight in red. So for that area, that dv is going to be equal to pi r squared dy, because it's still that kind of that cylinder shape. But in this case, it's going to be equal to pi x1 squared times dy. And what this chalks up to, if I want to find the area of this slice when I consider the hole, I'm going to take the area of the whole slice, including the hole, and then I'm going to subtract the hole. So what this means is the dv that I want in my equation is going to be equal to pi x2 squared dy minus pi x1 squared dy. So this first term right here, this is considering everything. This is considering the whole slice if there wasn't a hole. The second term right here, this is subtracting the volume caused by that hole in the shape. So actually I'll highlight it different and we can kind of go through together. So we're going to start with, we're going to start with the yellow. So the yellow term, this is the whole slice. This is everything, including the hole. And what happens is, to take into account the hole, we're minusing the volume of the hole. So that little green part, that's just right in the center here. That's just from the hole. And what you'll see is there's actually common factors of pi and dy. So dv is actually equal to pi x2 squared minus x1 squared times dy. So now we have an equation for dv, and if we look up here, we have y bar is equal to y. We can actually start subbing everything into this integral. So if I were to do that real quick, what I'm going to get is y bar is equal to the integral, and the first term is y squiggle, but we now know that is equal to just y. And then we got dv, which we now know is pi x2 squared minus x1 squared times dy. And all this is divided by the integral of dy. So the integral of pi x2 squared minus x1 squared times dy. So far, not too bad. We got our integral, and as we see, a little bit of magic happens. We got a pi on the top, a pi on the bottom. Well, those are constants, so they're going to cancel out. So now we're left with kind of two problems, and that one of the problems is going to turn into a bigger problem later, as you guys will see. But the first one is, of course, we need bounds or limits. So again, when you want to determine your limits, what you're going to look at is what you're integrating with respect to. So in this case, we have dy's. So therefore, we're integrating with respect to the y-axis. And if we look at the picture above, our y-axis, we know that our limits is going to be from 0 to 40. So right here, limits, we're going to have y equals 0 to y equals 40. So that's not bad. That was one of the easier ones. But now we're going to get into the real problem. We have x's, but we're integrating with respect to y. So now we need to figure out, okay, how do we change those x's in terms of y's? And typically what they do in these kind of scenarios is they give you the curve y equals, let's say, x squared or something. But now we don't have an equation. We just have pure geometry. So remember, we defined this one right here as y1. And this one as y2. So in order to solve for these, we know that these are linear. We can make equations y equals mx plus b. So all we have to do is make equations from these lines, and that's pretty easy. M is going to be the slope, so the rise over the run. And then b is just where it intercepts the axis. So if I extend this line down, we all know it's going to intercept the axis somewhere. And you guys are all geniuses, so I'm not too worried about you guys solving for that, because when you do, I'll let you guys solve for it because I know you guys know how to do it, but I'll give you the answer. What you'll find is that for x1, so for the first curve, which I'll highlight in orange, you should get y is equal to 4x1 minus 80. And again, I'm not showing you guys, I want you guys to figure this out. It's very important to solve linear equations, not only just for this course, but for a lot of courses. In the purple one, we have y is equal to 4/3 of x minus 40. So what I'm going to do is I'm going to take these two equations, we're going to bring them down, copy, paste. So then what I can do with each one of these is I can rearrange them. So the second one's x2. So if I wanted to, I can rearrange it. I can get x2 is going to be equal to 3/4y plus 30. And then the first one I can also rearrange. Get x1 is equal to y/4 plus 20. So now what I can do is I can just take those simple equations and substitute them right in. So what I'm going to get is this for my integral. My y bar is going to be equal to the integral 0 to 40 of y, because remember that y squiggle just turns into y, and then I'm going to go in brackets because it's going to turn into a real mess. And it's going to be x2 minus x1 squared, so we got 3/4y plus 30 squared minus, and then x1, so y/4 plus 20 squared. And I can end this and go dy. And of course we have to do the bottom integral. Oops. I'm going to put this line a bit further down. So I'm going to have the integral now, keep it at the end, still from 0 to 40. And I'm going to put in brackets because it's still a mess. 3/4 y plus 30 squared minus y/4 plus 20 squared dy. So now everything is perfect. We have our limits of our integral, but then as you see, we now also have everything in terms of y, and we're integrating with respect to y. So as I told you guys before, and I told my students many times, don't try and solve this, just throw it into your calculator. That's what calculators are there for. So I'm not even going to attempt to do this because that would waste so much time on your final, and you guys don't want to waste time on your final. But one thing I will recommend is don't try this all as one integral. As one equation. Solve the top first and then solve the bottom. Much better that way. So if I'm solving the top, my calculator gives me 1466666.6 repeating. And then when I solve the bottom, what I get is 58,666.6 repeating. And if you divide those two numbers, what you'll get is an even 25. So from this we can conclude that y bar is equal to 25 millimeters. I'm going to box this answer like this because that's my final answer. So again, a very tricky question. The concept is just making sure you get that slice right. And it's kind of tricky because they don't give you y1 or y2. You're going to have to determine those yourself. So I hope this helps you guys. If you guys are in 2019, I really hope that this helps your Wiley assignment, gives you guys some nice marks. If you're in 2020 and beyond, well, I'm not sure if you guys are even still using Wiley, but if you are, hopefully this helps you guys as well. So thank you guys all so much for listening, and I'll see you guys in the next video.